Don't forget to subscribe and ring that bell.
Hey, how we doing? We are going to be doing some calculus today, specifically the 2013 practice AP Calculus AB exam that College Board put out. We are going to start section 1, part B, and the first 9 of 17 questions. So problems 76 through 84, and whew, we get a graphing calculator. Some of the multiple choice problems without the graphing calculator were pretty brutal. We got through them. What was that? What type of calculator do I use? I have the mint green TI-84 Plus CE. I love it. So pretty. Look at it. But I put links in the description below. There are a slew of colors. If you're interested in grab one, go ahead and grab one. If not, hey, no biggie, no skin off my rear end. Let's do some calculus. Number 76. The graph of the function f shown above consists of 2 line segments and a semicircle. Let g be defined by g of x is the integral from 0 to x of f of t dt. What is the value of g of 5? First off, if you've seen any of the videos I've put up, you know how much I love graphs and tables and charts. Well, let's start with this graph right here. Okay, so what are they really asking us for? We need g of 5, which means g of 5. I'm putting a 5 in for this x, which means anywhere there's an x, it happens to be in the upper bound, also needs to be a 5. And if we've learned anything, okay, because we weren't sleeping in calculus class, about integrals, it's really just area under the curve. Okay, so the area under the curve from the 2 bounds, 0 to 5. So let's draw a line at x equals 0 right here, and a line at x equals 5. Well, we know this is a semicircle. They tell us that in the problem. And the area of a circle is pi r squared. But we have a semicircle, so we only have half of that. The radius goes from 3 to 5. I was going to go 1 to 3. Don't matter. It's still 2. So it's 1/2 pi. My radius is 2 squared. This is 4. 2 goes into 4 twice. That's 2 pi. Of course, I could use the calculator now. And if you want to use your calculator to check your simple math, go right ahead. No shame in that game. There's nothing worse than doing some good math and just screwing up on some simple algebra. Okay, so 2 pi is the area of that semicircle. Now let's worry about this, oh my goodness gracious, this nice slender triangle. Has a height of 3 and a width of 1. Of course, 1/2 base times height, which is 1/2 3 times 1, which is just 3/2. So I've got to add these. Okay, so it's just 3/2 plus 2 pi. I mean, 3/2. Wow, you know, normally they never give you decimals. They do sometimes in calculator problems. But look at it, they converted that. Okay, so 3/2, in case you didn't know, that's 1.5 plus 2 pi. And there you go. Choice D, simple one to start. 77. Now, this is one where you're going to use your calculator, not to check your work, but to perform the work, because look at those options they give me. Okay? 77. The volume of a sphere is decreasing at a constant rate of 3 cubic centimeters per second. At the instant when the radius of the sphere is decreasing at a rate of 0.25 centimeters per second, what is the radius of the sphere? Now, on the calculus exam, they're not going to give you the equation for the area of a circle or a rectangle or a square. If they do surface area of cones or things of that nature, they do. I'm surprised they give you the volume of a sphere. I'm shocked that they give you that. Okay, that's kind of a basic one, but if it's not basic, they will give you the equation. Here's the volume of a sphere. That's going to come in handy. So let's figure out what they're asking us. They're asking us, what is the radius of the sphere? So we're finding r, okay? And we know that the volume of the sphere is decreasing at a rate of centimeters per second. So if it's a rate, that means dv, or v prime, if you will, is -3 because it's decreasing by 3, all right? So they want us to know the radius right at the instant when the radius of the sphere is decreasing at a rate of 0.25. So it's not the radius, but it's the derivative of the radius is -0.25 because it's decreasing rate. They give us two rates here. All right, guys. All right. Here you go. So the first thing I'm going to do is I'm going to find the derivative of volume. Obviously, I need the derivative of volume. They give me the derivative of volume here, and they give me the derivative of my radius, which I will take when I take the derivative of my volume equation. So if volume is 4/3 pi r cubed, okay, the derivative of volume is 4/3 pi. That's a constant. We're going to leave it alone. The 3 comes down, r squared. But this is like implicit differentiation, okay? This is situational. Whenever we take the derivative of one of these terms, we've got to write either dr dt, which is what I like to use, or r prime. I don't do r prime a lot because when I do that, kids will ask me, where does this 1 come from? So I'm going to use, instead of using this, I'm going to use this. Okay, so this here is really dr dt. Okay, and if I do that, I really should do dv dt as well. I mean, but let's not talk about technicalities right now. You know what? I'm going to use r prime. Got it. I'm going to do it. So my 3 cancels with my 3, and I end up with 4 pi r squared r prime equals v prime. We need to find the radius, which is that boy right there, which means I should have the other two. I should have this unknown, and I should have this unknown. And we do have them right here and right here. So let's put those in and use our calculator to solve poo-poo, shall we? So v prime is -3. 4 pi, I need to know my r, that's what I'm trying to find, times r prime, which is -0.25. All right, well, you know what I'm going to do? I'm going to divide both sides by 4 pi times -0.25, because these will cancel. What I do to one side, I got to do the other. 4 pi times -0.25. I mean, if I want to do that math out, I can. I'm just going to have the calculator do it all. But now I have -3 over 4 pi -0.25 equals r squared. So if I want r, the last thing I got to do is just take the square root of it, right? These cancel. What I do to one side, I do to the other. So r is equal to the square root of that whole mess, and that's what's going in my handy-dandy TI-84 plus, yada, 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 yada. Okay, here we go. So it's a square root. That's square. It is a square root of a fraction. And on our fraction, we have -3 in the top, and in the bottom is 4 pi times -0.25. Okay, I think that's absolute. I'm looking at the bottom. That's what I got. 0.977. Well, if we round that 3 places, which is what all of our answers are, that second 7 will stay a 7. Okay, because the number after it's 2. That's approximately 0.977. And if it's radius, it's just centimeters, but this is multiple choice, so we don't got to worry about that. Number 78. Let f and g be continuous functions such that the integral from 0 to 10 of f of x dx is 21. The integral from 0 to 10 of 1/2 g of x dx is 8. And the integral from 3 to 10 of f of x minus g of x dx is 2. What is the value of the integral from 0 to 3 of f of x minus g of x dx? I am just going to kind of do some logic and write out my thoughts as we go so you can see it unfold. First of all, I'm going to kind of change this thing here. Okay, this is a constant. I'm going to pull my constant on the outside. So I've got 1/2 the integral from 0 to 10 g of x dx is 8. All right? If I multiply both sides by 2 to get rid of that 1/2, I've got the integral from 0 to 10 of gx dx is 16. Okay? So I have this. Okay, and I have this, both from 0 to 10. Why was that important? You look at my answer, I'm subtracting the two integrals, right? And then I have this where I subtract the two integrals. So I'm going to subtract the two separate integrals that I highlighted in blue and make them one integral. Okay, so the integral. Notice that in both of these, the f comes first. And in subtraction, order matters. So the integral from 0 to 10 of f of x dx, well, that's 21. So I'm just going to write that below here, 21. I want to minus the integral from 0 to 10 of g of x dx. And that we just figured out as 16. So this is 5. So instead of writing them as two separate integrals, I'm going to write them as one. Okay? So I basically have the integral from 0 to 10 of f of x minus g of x dx. That equals 5. Okay, we just figured that out. That's good. We're doing good. Here's the awesome part. I know, okay, if I were to represent this as a graph from 0 to 10, right? And there's some curve, which is f of x minus g of x. This area under the curve from 0, yep, I thought I changed the color, from 0 to 10, that's an area of 5. This whole thing is 5. All right? They want to know the area from 0 to 3. So I got to go from 0 to 3, which means I want to subtract out all this area from 3 to 10. Okay? We know the area from 0 to 10. We want to subtract out the area from 3 to 10. Oh, look at that. They give us the area from 3 to 10. If this whole thing is 5, this whole entire thing is 5, and we subtract out from 3 to 10, which they tell us is 2. Okay, well, that leaves us with 3 here, because 3 and 2 give us our total of 5. So the answer, okay, if we want to know from 0 to 3, is 3. That's really just kind of using your brains. You really don't have to do too much like math there, but you just got to follow that logic as we go. 79. Oh, more graphs. Love them. The figure above shows the graph of f prime, the derivative of f. If f of 0 equals 0, which of the following graphs could be the graph of f? Okay, so if I look here, first of all of these have the coordinate 0, 0 in them. Okay, so I don't know. It's stupid that they tell us this right here. That's just saying the graph's got to go through that point, the origin, and they all do. So that's really not going to be a big help. So what I'm going to do is I'm going to look at the graph up here, and I'm immediately going to say this is the derivative of f, which is the slope. My y value is going to be the slope. of f. Okay, it's a slope of f. All right, so anytime my y value is positive, when it's above the x-axis, I'm going to have a positive slope for f. And anytime it touches the x-axis, where y is 0, I'll have a slope of 0 for f. And anytime it's below the x-axis, my y value will be negative, which means my derivative is negative, which means my slope is negative. So let's take a look here. Every part that's green is a positive slope. If it's blue, where it touches here and here, it should have a slope of 0, right? And where it's red, it should have a negative slope, 0 slope again, then back to a positive slope, okay? And then it touches here again, so I should have a slope of 0 again. So there's going to be 4 times, those 4 blue zeros, where my slope is 0, where it will look like a horizontal line, meaning the graph of f, I'm just going to sketch it. At this point, it's flat. At the point where it's 2, it's flat. At 3, it's flat. At 4, it's flat. But it's going to increase between the first 2 flats. Okay? So from this point to this point, I have a positive slope. So it starts out flat. It goes up and gets flat again right here. Then it's going to decrease till the next time it gets flat. So then it's going to decrease the next time it gets flat. Okay? Then it's going to increase the slope again until it gets flat a third time. So then I'll increase it. So my graph should kind of look like that. Okay? So it should go up, down, then up. So if I compare my graph, it's definitely not this one. Okay? It doesn't end like that. Okay? It goes up, down, then up. So it goes up, down, then up, and it should stop. It doesn't have this. It's not this one. Okay? Up, down, then up. Well, it's going to go down again. So it's either C or D. It goes up, down, then up. And this one goes up, down, then up. All right, now you're looking at the way I drew it and saying it must be C. But let me explain to you the difference between C and D and why the answer is C. And it all lies within this last point. Where my graph ends, notice my slope should be 0. Okay? Look at C and D. C, it flattens out here. That is a slope of 0. This is going up. That's not a horizontal slope. That's a positive slope where it ends. So my choice is C. Number 80. For time t greater than or equal to 0, the position of a particle traveling along a line is given by the differentiable function s. S, okay, of t. So s of t is position. Okay, if s is increasing for 0 to 2, t values between 0 and 2, and s is decreasing any time t is greater than 2, okay, which of the following is the total distance of the particle travels from 0 to 5? I have said this time and time and time again. All right? First of all, let me sketch position. We go from 0 to 5, right? That's what they give us here. Yes. So from 0 to 2, my position is positive. So if I go to position, it's positive, right? And from, we'll go like this, positive. And from 2 to 5, anytime bigger than 2, it's negative. It's decreasing. So it's, okay, it's decreasing. All right? Actually, yeah. Well, we could do that. We could do that. We could do that, or we could do, it says increasing or decreasing the position. So that means actually change in rates. That means from 0 to 2, it's increasing position, 0 to 2. And then after 2, it's decreasing. All right? But, okay, area under the curve of velocity. Okay, because velocity is the change in position. Decreasing and increasing represent change in position, which is velocity. Okay? The change in position is velocity. Okay, increasing and decreasing. The area under the curve, okay, would give me position, right? Give me total distance or displacement, okay? So it's like I'm integrating velocities, like integrating s prime. So you can see that's why we have a lot of integrations of s prime here. But here's the kick. They don't want displacement. If I have a graph and velocity goes up, then down, I want it all the area underneath the graph to be positive. So I want this area to be positive, this area to be positive, and this area to be positive. Right now, if I integrate this from 0 to 5, okay, integration means this would be negative and this would be negative. So how do I integrate something to make it all positive? Absolute value. Absolute value means I don't care if it's negative, still consider it to be positive. Still consider it to be positive. Choice E. 81. A cup of tea is cooling in a room that has a constant temperature of 70 degrees. Well, that's nice. Tea. I prefer coffee, but tea is supposed to be healthy. If the initial temperature of the tea at time 0 minutes is 200 degrees, and the temperature of the tea changes at a rate of R of t, which is negative 6.89 E raised to the negative 0.053 T, degrees Fahrenheit per minute, that is, what is the temperature to the nearest degree of the T after 4 minutes? So basically, R of t is in degrees Fahrenheit per minute. They're asking us what is the just temperature, not rate. So they're asking us about what is just degrees Fahrenheit, which means I got to integrate. I'm going backward. Okay. So, if I integrate, remember, based on the last problem we did, if I integrate without absolute value, that's displacement. That's just the change. Okay? Total distance or total degrees Fahrenheit is if I have the absolute value bar. I'm not doing that. I'm going to integrate R of t and see where it is after the 4th minute. Okay, if I start at 0, what is the change or the displacement in temperature after 4 minutes? Which, by the way, it started at 200. This will be decreasing, so it will be going down. This will be a negative number, but I started at 200. Okay, so if this value gives me, I don't know, negative 30 or something, my t isn't negative 30. It would be 170 because I started at 200. So I got to make sure I have 200, and I add that to my negative value that I get for my integral. Thank God we get a calculator. Bang, bang, ding, ding, dong. Do this, erase that from the previous problem, turn this on. I'm going to start my 200, and I'm going to add, okay, the integration, which is math 9, in these wonderful calculators from 0 to 4. My equation for RT, which is negative 6.89. And make sure you type this in right because you've got all your logic down. It would be a shame if you made a mistake typing into the calculator. So that's E raised to the negative 0.053. My variable is X to the X. Bam. 175.165. There you go. I'll put that right here. 175. So they said, what is the temperature to the nearest degree? Whole number. That's just 175 degrees. Choice A. Man, you really don't get to use the calculator too much for these things. But the problems like this where you can just bang them out, man, it's nice. 82. The derivative of the function f is given by f prime of x, which equals x cubed minus 4 sine of x squared plus 1 on the interval from negative 2.5 to 2.5. At which of the following values does x have a relative maximum? Okay, let's establish what we're going to look for on the calculator when we first use the calculator, whatever. You know what I mean. Let's figure out what we're looking for. Relative maximums. That means the first derivative is going to go from a positive value to a negative value. Okay, that's it. That's where maximums happen. Now, I'm graphing the derivative of f. I'm graphing f prime already. So on my graph, I don't know what it's going to look like, something like that, who knows. If this is the derivative, remember, it's positive anytime it's above the x-axis because my derivative is the y value. And it's negative anytime it's below. So if I want it to go from positive to negative, I got to follow my graph. Okay, well, it's negative below, and it's positive here. So right here would be a negative to positive value. I don't want that. I want positive to negative. So let's continue. It's going to go. So then here it changes here. So at this point, I go from a positive derivative to a negative derivative. That's what I'm going to be looking for when I graph my derivative right here. Okay, I'm going to go from the positive y values to the negative y values. That will be a positive slope to negative, and that's where my maximum will be. I'm going to graph that on this interval from this x value to this x value. I don't care about anything outside that interval that they give me. So let's go to y equals. Let's put in something fancy there, fancy pants. X cubed minus 4 sine of x squared plus 1. Don't forget that plus 1. Okay, that looks like what I want. Is that what I'm going to do? Yeah, that's it right there. Okay, we're good, we're good. Now let's go to my window. I just want to go from negative 2.5 is my x min. Oh, not 0.25, but 2.5. Negative to positive 2.5. There you go. Let's graph this and see what I get. Okay. Remember, we want to go from above the x-axis right there to below right there. Above. That's it. Okay, this is good. So I'm just going to do this. Here in green is where I have a positive y value. And remember, my y is the first derivative, so I got a positive first derivative. I got a positive first derivative right here. Yep, that's right. That was my bad, kids. This is all negative in red, okay? Which means this is negative in red. The only place that I go from a positive value to a negative is I'm going left to right, okay, is right here. That's the only place. It's a positive to a negative, okay? This one goes from negative to positive. And this one also goes from negative to positive. I want the positive to negative. So I got to find my zero function. I got to find out what value that is. Okay? I got to find out what value that is. So let's do this. Which of the following x values? Yes. So I go second trace, and I calculate the 0. And I just got to go to the left of it. Oh, that's right there. Enter. I got to go to the right of it and hit enter. And then I hit enter one more time. Before I hit enter one more time, the color edition, or this is color silver edition. This is a TI 84 plus C for color, but it's a silver one. It's the digital one. I can't change the color of the calculator. It's gray. Now, you see how I put the arrows there and those vertical little dashed lines? And you got the colored lines. I could have graphed that any color. That's what this calculator does that the TI-84, the regular edition, does not do. And I'm telling you, it is worth it to have these. I'm not trying to push the product. But if it was my kid, I'd give him this calculator. In fact, I did. I got him the TI-84 Plus C, and I got him the color edition. He likes blue, so his calculator is blue. He loves it. Now, let me hit enter one last time. There it is, 0.542, okay? So that's the only place. 0.542, that will stay a 2 because the number after it is smaller than 5. Choice E. It was longer to explain what I was looking for than to actually find it. But we need the explanations to understand. Oh, man. The number of graphs and tables? Wunderbar. I love it. 83. The table above gives selected values for a continuous function f. If f is increasing over the closed interval from 0 to 3 inclusive, which of the following could be the value of the integral from 0 to 3 of f of x dx? All right. Oh, my neck, my back, my elbow. No, okay, so here we go. The table above gives selected values for continuous value. If f is increasing over the closed interval from 0 to 3, which of the following could be the value of this? So basically, it's the area under the curve here from 0 to 3. Okay, this is what I'm going to do. This is what I'm going to do, kids. This is what I'm going to do. So we got... I'm going to just kind of sketch this, if you'd allow me to just sketch this. And there might be several different ways that you can do these problems, but this is just the way that I like to do the problems here, okay? I'm going to plot these points. Oh, my God. 0 to 3 goes all the way to 54. That's okay. We'll do this by half. So 0, 1, 2, 3. Here's a half. Here's 1.5. Here's 2.5. And I go all the way to 54. Oh, God bless you. And I start at 4. Then I go to 10, which would probably be what? Here, 10. Here is 4, we'll call that. Then we go to 18. 28. Oh, my God. This is very bad, the number-wise. 40 will be closer to here. 40. So I got 0, 0, 0.54, 110, 1.5, 18. Okay, 2 is 28, 2.5 is 40, 3 is 54. There. And when I connect these, I kind of remember it's not really to scale because the y-axis isn't to scale. So here's the huge thing right here. Could, and I don't have to draw this, but I like to sometimes give visuals. I could try and use LRAM, which would go here, which I'm doing in red for this segment. But then I'm missing above that, this little triangle here, I'm missing this area. I could do RRAM, which if I do the next segment in green, okay, I do that, but now I've got too much area. Okay, well, I could do MRAM, which is in the middle, and it looks like maybe what I'm missing here might be the same as this. But you should know in calculus that the trapezoid rule is more accurate than any of them. It's not exact, but it's more accurate. So when it says could be, we're going to do the trapezoid rule for all these things. So that visual is just to kind of explain to you when we're estimating area under the curve, not exact, that the trapezoid rule is more accurate than LRAM, RRAM, and MRAM. So what the trapezoid rule tells me is I take my width, or some people say height, and I divide it by 2, and I take all my y values and add them up. Y0 plus, and then I got to double all the middle ones. The last one, whatever it is, doesn't get doubled. All right? So I call these my bookends. I don't double the bookends. I just double everything in the middle. All right? So let's start to separate these. The width is going to be 0.5 for all of these, which makes it nice. Okay, the width is 0.5. Okay, let's just, here we want, there we go. We got 1, 2, 3, 4, 5, 6 sub-intervals, which will be trapezoids. And my width is 0.5. So I take my 0.5 and put that over 2, okay? And I start adding all my y values. 0, that does not get doubled, plus 2 times 4, plus 2 times 10, plus 2 times 18, plus 2 times 28, plus 2 times 40, plus this is the other bookend that does not get doubled. I'm going to put that in a calculator, and it should give me an answer. Okay. Here we go. Get out of here. Close that out. I'm going to say parentheses 0.5 divided by 2. Okay, the reason I'm doing that is I don't want my answer to be in fraction form, so I'm not going to put it with a fraction function here. And now, my first thing, it's 0, that doesn't get doubled, plus 2 times 4. And I just got to go down the line here and make sure I don't mess anything up. Plus 2 times 10, plus 2 times 18. Okay, keep on peeking at that calculator to make sure it's good. Plus 2 times 28, plus 2 times 40, plus, now this is the last bookend, the 54, that does not get doubled. 63 and a half. 63 and a half, and I believe that is actually one of our answers. Well, actually, I lied when I said it's one of our answers. Could be. That's the closest approximation. 63 and a half is closest to 62. That's B, choice B. Now, some of you might say, well, I don't like that my answer isn't one of the ones listed here. But this is an estimate, and that area under the curve for trapezoid rule is the best. What I don't like about this problem here is if I erase this all here, instead of using the trapezoid rule, okay, remember when I drew that picture to start this problem, we said the midpoint rule is better than the LRAM or RRAM. So MRAM would be the best. If I looked at all these terms and I said, well, if I go from 0 to 1, I have a clear-cut middle, which is 4. And then if I go from 1 to 2, I have a clear-cut middle, which is 18. And if I go from 2 to 3, I have a clear-cut middle, which is 40. So I'm going to use a width of 1. How come? Just so I can use MRAM. Okay? Just so I can use MRAM. If I went from 0, okay, to 0.5, I don't have a middle value, do I? So I've got to extend the width of my subinterval so that I have a middle. And what do I do when I do MRAM, LRAM, and RRAM? I add up all my Y values and multiply by the width. So 4 plus 18 plus 40 times the width, which is 1. The subinterval width of each one of these is 1. 58 and 4, there's where your 62 comes from. Okay, there's where your 62 comes from. But I tell you what, as a math person, if I can't find it exactly, I want the closest I can get to it. And the trapezoidal rule, I mean, I don't know. I think the trapezoidal rule is a lot closer than the MRAM, but hey, that's just me. That's what I use to get my 62, the trapezoidal rule. But if you're one of these people that's like, it's not the right answer, though. Well, the right answer would be using the MRAM. That would give you the number on the button. But trapezoidal rule gets you closest to that value anyways. Oh, man. When was the last time I had a true-false question? 84. Another graph. Look at us go. The graph of the function f is shown in the figure above. Which of the following statements is true? You have 5 options. 4 of them will be false. 1 will be true. All right. So let's take a look at these one at a time. And we'll look at the first one. F of A is 2. That's a coordinate. When x is my A value, my Y value, it's not 2. It's actually 1. This should be 1. So this is false. F is continuous at A. Do I got to explain to you that there's a hole at A? So it is not continuous at A. So this is false. The limit, okay, now we're starting to get into the tricky ones here. The limit as x approaches A is 1, which means as I follow my graph from the right side and go toward an x value of A and the left side, okay, in case you didn't know, this vertical line is x equals A. So as I approach that from both sides, it approaches a value of 2. It can be a hole there. I don't want to know what it exactly. I just want to know what it approaches. It's pointing toward a y value of 2, not 1. That's false. Well, that helps us prove that, well, D is right. It is 2. That's what we just said. So this is the one that's true. And the limit as x approaches a does not exist. That is false. Just because there's a hole there doesn't mean that the limit doesn't exist, okay? You can have a limit that a removable discontinuity is a hole. You can absolutely have that. It's 2. So choice D actually disproves choice E. So that's false as well. We are done. You can see how those sweet calculators help out a lot. And hey, I will see you when we run it back for the next 8 problems for section 1, part B. We'll see you.
Don't forget to subscribe and ring that bell.